This is Robert Capetta from the University of Illinois at Chicago, and this lesson is on the alternating series test. So what is an alternating series? It has -1 to the k or -1 to the k plus 1. -1 to an even number is +1. -1 to an odd number is -1. So the signs alternate, negative, positive, negative, positive, negative, positive. So I call this a sign flasher in either case. -1 to the k or -1 to the k plus 1 is a sign flasher. And then it is multiplied by something else. Now, this something else, for the sake of argument, I'm just going to call b sub k here, although I'm never really going to use that notation. So a sub k is the sign flasher, whether it's -1 to the k or -1 to the k plus 1 times b sub k. But what I'm going to talk about more often is the absolute value of that sequence. And the absolute value of the sequence is the thing multiplying the -1 to the k, where b sub k is positive. So we're going to establish some rules. If these conditions are met, the alternating series will converge. So what must happen? First of all, the series has to alternate. You need to see negative, positive, negative, positive, negative, positive, negative, positive. And you can see that with -1 to the k or -1 to the k plus 1. The second condition is once I remove the sign flasher, so I take the absolute value which eliminates the sign flasher, the limit of that new sequence must be 0. And it must go there in a decreasing fashion. The next term must be smaller than the previous term. So a sub 7 is smaller than a sub 6. A sub 11 is smaller than a sub 10. So the series is decreasing, it's monotonic, it's decreasing. If the limit of the absolute values is 0, and if it's decreasing, and if it alternates, if we hit those three conditions, then we know that the alternating series will converge. So it's almost a kth term convergence test. Remember, we have a kth term divergence test. If the kth term does not converge to 0, then we know that the series diverges. But in this case, in a sense, if the kth term goes to 0, in a decreasing fashion, we will argue that the alternating series will converge. So let's look at an example. We want the sum as k goes from 1 to infinity of -1 to the k times 5 over 2k plus 3. Does it alternate? Now, just to show you, I went ahead and I plugged in various values for k. -1 to the first times 5 over 2 times 1 plus 3 is -5 over 5. Plugging in 2, -1 to the second times 5 over 2 times 2 plus 3 is +5 over 7. Plugging in 3, -1 to the third times 5 over 2 times 3 plus 3, -5/9. Plugging in 4, -1 to the fourth, +1 times 5, 2 times 4 is 8, plus 3 is 11. I just wanted to show you how it's alternating. -5 over 5, 5 over 7, -5 over 9, 5 over 11. But really, this thing right here, -1 to the k or -1 to the k plus 1, will tell us that the series is alternating. So that's our first condition. What else do we need to look at? We need to show that when we strip off the sign flasher, when we look at the absolute value, that the limit of that absolute value is 0. And then we've got to show that the next term is smaller than the previous term. Those are the other two conditions that we have. So indeed, a sub k, the series is -1 to the k times 5 over 2k plus 3. In our discussion before, we said a sub k was -1 to the k times b sub k. But I'm going to just call it the absolute value of a sub k. When I do that, I eliminate the sign flasher. So absolute value of a sub k is 5 over 2k plus 3. And I want to know what is the limit as k goes to infinity of that. And indeed, that's 0. As k gets large, 2 times a large number is large, plus 3 is still a large number, 5 over a large number is going to go to 0. So the limit of the absolute values is 0. The last condition, though, I've got to show is that it's decreasing to 0. But so far we've taken care of the fact that it's alternating, and we've taken care of the condition that the limit of the absolute values has to be 0. So the one last thing we've got to show is that these absolute values decrease. That a sub k plus 1's absolute value is less than a sub k's absolute value. So again, we're back here. The absolute value of a sub k, eliminating the sign flasher, 5 over 2k plus 3. A sub k plus 1, replacing the k with k plus 1. 5 over 2 times k plus 1 plus 3. 5 over 2k plus 2 plus 3. 5 over 2k plus 5. Now you notice I have these two fractions. The tops are the same, the bottoms are different. The bottom is bigger for a sub k plus 1, which makes the entire fraction smaller. So indeed, 5 over 2k plus 5 is less than 5 over 2k plus 3, which tells me then that the absolute value of a sub k plus 1 is less than the absolute value of a sub k. So that's my third condition. Putting all those together, we can conclude what? The three conditions were met, so the original series converges by the alternating series test. Now, is it absolutely convergent? The series is absolutely convergent if, when we take the absolute values, it's still convergent. So if the sum of the absolute values converges, then we say the original series is absolutely convergent. This is our idea. So if something is absolutely convergent, we know for sure that it's convergent. Absolute convergence implies convergence. So we need to take a look at what the absolute values would be. So this was our original function, our original series. If we take the absolute value of that, we lose the sign flasher. So the absolute value of a sub k is 5 over 2k plus 3. So the sum of the absolute values is the sum of 5 over 2k plus 3. This is to check to see if it is absolutely convergent. What can we say about that? We need to use the limit comparison test. So 5 over 2k plus 3. The top is basically like 1. The bottom is basically like k. Highest power of k on the bottom, k to the first. Highest power of k on the top, there isn't one. Maybe call it k to the 0, 1. 1 over k is what we're going to limit compare this to. So I'm looking at the sum of the absolute values to see if it's absolutely convergent. I'm going to use capital A sub k and capital B sub k to differ from the sequence A sub k I talked about up there. So with the limit comparison test, we take the limit of A sub k divided by B sub k, and we hope to get a positive finite number. If it's a positive finite number, both series are of the same type. The limit of a sub k over b sub k is the limit of 5 to the 2k plus 3 divided by 1 over k. Invert and multiply times k over 1 gives me 5k over 2k plus 3. Dividing the top by k, I get 5. Dividing the bottom by k, I get 2 plus 3 over k. As k gets large, 3 over k goes to 0, and my limit is 5/2. I'm happy because that is a positive finite number. If I have a positive finite number, both series are of the same type. This series, the sum of 5 over 2k plus 3, would be the same as the series, the sum of 1 over k. But we know something about the sum of 1 over k. So again, this is what we're dealing with. And we know that the sum of b sub k is the sum of 1 over k, which is a divergent series. It's the harmonic series. 1 over 1 plus 1 over 2 plus 1 over 3, etc. Starting at 1. So don't be concerned that the index there starts at 0. That's not really an issue here. What can we argue then? The sum of the a sub k must be of the same type. Since the limit comparison test gave us a positive finite number, both series are of the same type. Sum of 1 over k diverges, therefore sum of 5 over 2k plus 3 also diverges. So the absolute values diverged, not absolutely convergent. So the original series was not absolutely convergent. When we took away the sign flashers, it diverged. So when that happens, so the original series was convergent, but it's not absolutely convergent. When that happens, we say the series is conditionally convergent. So an alternating series can be one of three states. It can be absolutely convergent, it can be conditionally convergent, or it can be divergent. Those are the three things we can check. So let's take a look at this example. This is alternating. We see it has negative 1 to the k plus 1 of 7 over 5k cubed plus 2k plus 3. Is it absolutely convergent? In other words, if I remove the sign flasher, does it converge? Is it conditionally convergent? With the sign flasher, it converges. Without it, it doesn't. Or divergent. So we'll take a look to see what's going to happen here. We still have our three cases to determine convergence. Does it alternate? Does the limit of the absolute value give us 0? And does it decrease? Is the next term smaller than the previous term? This is what we're starting with. It does alternate. Negative 1 to the k plus 1 is starting at 1 this time. Negative 1 to the 1 plus 1. Negative 1 to the 2 is positive 1. Negative 1 to the 3 is negative 1. negative 1 to the fourth is positive 1. So it does alternate. So we have condition 1. Condition 2, take its absolute values. Is the limit 0? Well, the absolute value of this removes the sign flasher. It's just 7 over 5k cubed plus 2k plus 3. Now what's the limit as k goes to infinity of that? The limit as k goes to infinity of 7 over 5k cubed plus 2k plus 3? That's 0. Condition 2 is checked. Now can we conclude that the next term is smaller than the previous term? A sub k plus 1, plug in k plus 1, 5 times k plus 1 cubed plus 2 times k plus 1 plus 3. That denominator is bigger than this denominator, so yes. If that's the case, we can conclude that a sub k plus 1 is less than a sub k, so condition 3 is indeed checked. So this original series converges, but is it absolutely convergent? If I remove the sign flasher, does it still converge? So the sum of the absolute values is this, 7 over 5k cubed plus 2k plus 3. Limit comparison test again. What am I going to use? A sub k is what's given. B sub k, what is this really? Again, upstairs just 1, downstairs highest power k cubed. If I take the limit as k goes to infinity of a sub k over b sub k, limit as k goes to infinity of this divided by this, invert and multiply, so multiply times k cubed over 1. So I get 7k cubed over 5k cubed plus 2k plus 3. If I would divide by k cubed, top and bottom, I hope it's obvious that that limit's going to be 7/5, which is a positive finite number. When we have a positive finite number, both series will be of the same type. What do we know? There's our positive finite number. I know the sum of 1 over k cubed, bk, converges by the p-series test. The exponent is 3. 3 is more than 1. That's going to converge. Therefore, the sum of the absolute values also converges by the limit comparison test, because both series are of the same type. So when I remove the sign flashers, the absolute values still converged. So the original series converged by the alternating series test. The absolute values converged by the limit comparison test. So what's my conclusion? The original series is absolutely convergent. Let's take a look at one more example. Sum is of negative 1 to the k plus 1 times 3k plus 7 over 8k plus 11. It alternates. I see negative 1 to the k plus 1. Again, k starts at 1. 1 plus 1 is 2. Negative 1 to the 2 is 1. Negative 1 to the 3 is negative 1. Negative 1 to the 4 is positive 1, etc. So it does alternate. But if I take its absolute value, I have 3k plus 7 over 8k plus 11. What can I say about that? What is the limit as k goes to infinity of that? Well, if we would divide top and bottom by k, we'd have 3 plus 7 over k, 8 plus 11 over k. That goes to 3/8. That is not 0. Condition 2 is violated. The limit of the absolute values is not 0, which means the limit of a sub k also not 0. If the sequence does not converge to 0, what's our conclusion? The series diverges by the kth term divergence test. So the original series that we have is not conditionally convergent, is not absolutely convergent. It is actually a divergent series. So that will conclude this lesson on the alternating series test.